One of our speakers is not even here.
Oh, I want to go, like,
I hope he shows up.
oh, I didn't go last time. We were playing on it.
That's what I did. I'm waiting one day and we just gotta get.
And then coming in the back way,
After I.
and then the back way is so much better than going
Yeah,
in the front.
yeah, you come in from the
front way, it's like
on the side.
Yeah.
Well,
Well,
the trailer's long.
no, the road is a lot better than.
Oh, yeah,
There's a lot of like right turns and then traffic roads and stuff, the way from the Texas side. So there's some small advantage.
Yeah.
And it's not great doing that second.
I haven't seen them before.
And I do like it.
Uh-oh. I'm in trouble here. I got act normal. All right, Doug, here it is. It's just arrow through or. Okay. And keep the pointer in the presentation. We'll keep the presentation. Let's see. So I should be able to enter the backspace, right? Let me try it. Enter? Yeah. Backspace. Uh-oh. Try back arrow.
Yeah, better next time. Just in general, you get a lot of next.
How come I can't back up? That's a good question.
I've never been in, so I can't really say. It's just not my kind of thing.
What about down there? Will that work? I can't seem to get to it. How'd you do that? Okay, on the bottom corner, there's arrows here. Okay, got it. Thanks. Okay, that's important. So is it live there? Yeah, it's live. Okay.
Once you're there, you can sort of get a cell phone connection, but on the way there, there's a lot of bad stuff.
Yeah, I think where you're there.
Somebody you know?
Jerry.
So we did WhatsApp.
Oh, okay.
Okay, so you need to get hooked up on WhatsApp as part of,
That's over.
yeah, it's texting through the internet.
I'm trying to remember, I think I did because I did, my phone service, I had a service. I sort of, what was the best fit? I was able to do but the second you get off the property.
And you can only get in certain spots.
Hi, you're Doug.
I am Doug.
Hi, I'm Linda Bridge.
Oh, Linda Bridge.
I work with Lynette.
Oh,
Yeah. It's my husband, Jeff. So
Hi.
we finally made it.
Great. Yeah, she's actually mentioned it.
Oh,
I can't remember what about. Just your name sounds familiar.
she worked with my dad.
You worked with your dad?
She used to. I mean, he's passed,
Okay.
because
But you work with her now?
he's older than you guys. Yeah. She worked with him back in high school.
Okay. Yeah, I remember your name, but I can't remember.
Yeah.
That's how you-
Yeah, I started in February.
Oh, so you're new to the group.
I'm new to the
Okay.
group and I get her test plans and write the
Excellent.
tests.
Well, I'm glad you came,
Yeah.
because otherwise, we usually have about 70 people. I don't know where everybody is.
Oh, wow.
Yeah, this is really,
Oh,
hey,
interesting.
David?
Well, all right, I'll let you get.
Okay, yeah, I gotta
nice
start.
and stuff,
Thanks.
yeah.
Okay, it's 7:30 and what? Are you
I was
going?
just coming to say hi, but
Hi, Rick.
go ahead.
I gotta start. I gotta be on time. Astronomers are always on time, right?
I've never seen that actually happen. Is that new or?
Well, okay. So anyway, welcome to the August meeting of the Johnson Space Center Astronomical Society. I think you guys can tell from looking around, this is probably the least number of people we've ever had at a meeting, but whatever. Anyway, so welcome. And let's see, before we get started, we always like to say, is anybody here for the first time? And tell us your name. Let's see how you found out about us and what your interest is in astronomy. You guys.
Jeff and Linda, she works.
I work with Lynette Holland.
She works with my wife.
Yeah, and just started there 6 months ago or so. And we have telescopes.
Oh,
She mentioned telescopes, so
yeah.
we finally made it.
So Linda and Jeff,
It's my husband Jeff.
but his name's Jeff, right? So what kind of telescope do you have?
I've got a 6-inch RCT
Oh,
and you've got a,
Williams orange.
Yeah.
Which I'm a newbie on it, but I'm excited to get going. I've got done a little bit. He's done way more.
and RC, you mean Richie Cretion? RC, so you got one of the Astrotech Richie Cretions?
it's the IOP program.
Oh, okay.
Yeah.
Is that made by the same company or is it something different?
It might be.
Okay, well, that picture was taken actually with a 8-inch Ritchie Cretion.
Cool.
Yeah, yeah, so it can be done.
Oh, yeah.
Yeah.
Mine was the pointer in the middle.
Well, yeah, now the pointer wasn't really there. That's, but other than that,
It was a planetary under-
yes. But you work on it for about 20 years and you'll be able to take a picture.
20 years.
Well, at least that was my experience, but you know, there's other people like Stan. How long have you been doing it?
About 18 months.
Yeah, see, that Stan, there's something wrong with Stan though. So somehow he's getting great pictures. He's only been doing it for 18 months, but I don't know. Maybe he's a natural. Yes. Anybody else? First time here, right over here.
Yeah, so, good evening. My name is David. I work at Johnson Space Center as an engineer on the Gateway Space Station. My interest in astronomy is every time I go to public events to represent Gateway, the public expects me to know everything about astronomy, which I don't. There was a kid who asked me how many moons Jupiter had. I didn't know. More than one. So I think I should probably have some better knowledge of astronomy, so that's my interest.
Great, David, right?
That's correct.
Okay, welcome. You came to the right place. We have lots of things that you can participate in, learn all about astronomy here. Anybody else? First time here. I think there's some really cool people up there in the top row. Who are those guys? You gonna tell us your names? You just want to wave at us? That's okay. Do you want to tell us your names?
Dominic?
Dominic?
He has a YouTube channel that's all about space.
Good. Who's your little brother there? What's his name? Are you guys somehow associated with Paul? Yes, I think this is Paul's fan club here is what that is. I think that's going on there. And what this nice lady here, what's your name? Oh, he didn't find you outside somewhere and ask you to come in with him? Great. Well, Paul's one of our speakers tonight, so good. He brought his fan club with him. Great. Glad you guys are here. All right, who else? First time here, willing to admit. Look, who's that guy walking across the top there with that funny hat? See, he put his hat on to disguise himself. That's Mark. Okay, anybody else? First time here? I don't think so. Oh, I know you. Madison, right?
Second time.
Yes. Okay, that doesn't count. Only first time. Second time, you're already part of the group. You remember now. Okay, very good. Glad you guys are all here tonight, and we will press on. Here's our agenda for this evening, and we're not gathering online questions. Is that correct? Yeah. Yeah, it's fine. Okay, so if you're online, welcome, but we can't see your questions tonight, so sorry about that. Okay, there's our agenda. Okay, so we have an email distribution, and up there you see Al is holding up his clipboard. If you'd like to get on one of our email distributions, you can tear off one of those little things, and one of them is for members or for meetings only, and one of them is for general distribution. The top one is for meetings only, and the bottom one is for general everything. So you can either take a picture of that and send in your email address to those and get on our list, or you can just grab off one of those tear off things from Al and get on our distribution list, and you will know everything that's going on here. Okay, see, Linda's got her phone out. She's taking pictures. You done? All right, she got it. Okay, speakers. We have two speakers. Paul and Phil are going to be our speakers. Thank goodness. Otherwise, we wouldn't have any speakers. And when you guys are up here, use this little mouse pointer thing so the guys online can see it. Just use a mouse pad. Trevor says don't let it go off the presentation. And when you get up here, you see it's just a small part of the screen is the presentation. And for the people to hear us, the mic going out on the stream is the one in the laptop. The one for the people in the room is this one. So you got to kind of stay in this area. If you wander off somewhere, then people online can't hear you any longer. So you got to kind of stay in this general area so that you can be heard. All right. So our main speaker tonight is Phil Stewart, and there he is wandering down here. And before Phil comes up here, I'm going to tell you a little bit about him. And I'm going to warn you, Phil, I got lots of questions about your presentation. I got to see Phil's presentation ahead of time, and I don't understand it, so I'm going to be asking him things about it. Yeah, so he didn't put enough words in there for me. Okay, Phil Stewart became interested in astronomy as a teenager in the mid-70s. That's 1970s. 70s. He worked for the U.S. Postal Service for 4 years while majoring in art part-time at Tarrant County Junior College. Phil became interested in aerodynamics while trying to measure the drag coefficient on his 1979 Corvette. Do you still have that Corvette? Oh, man, too bad. Okay. Anyway, after leaving the post office and combining his interest in space and aerodynamics, he completed a degree in aerospace engineering from Texas A&M University. Woohoo! Yeah, we have one of our sons went to Texas A&M University, so you're okay. He then worked for NASA JSC for 38 years in the aerosciences branch. That's good. Retired at the end of 2022, Phil is finally ramping up his astronomy hobby. So join me in welcoming Phil Stewart. So to forward, you hit the enter. To back up, there's these little arrows down there in the Trevor and I just discovered this tonight.
Okay.
You can back up that way.
So the arrow keys don't work?
They weren't working.
To go forward, you can enter, but to go backwards, it doesn't work.
Okay.
So, yeah, okay.
I'll try not to go backwards.
They used to work. I don't know why they don't work anymore.
All right. Well, what I'm going to talk about is something called a Solex spectroheliograph. And it's just an instrument that you can take some really cool pictures of the sun with. And I built one of these, and it's a whole lot of fun, so I thought I'd share it with everybody. Now, since we're talking about the sun, I have to talk a little bit about solar safety. And the main thing with the Solex is it's not designed to be looked through. It's not eye safe. It's photography only, so don't look through it. If you look at a raw picture from it, that's what I've got in the lower right corner. It doesn't look anything like the sun. So if you look through this thing, you wouldn't see anything worth seeing, till your eyes burned out. But it's just don't look through one. All right, this is what a Solex looks like. The name stands for Solar Explorer, and it's a type of instrument called a digital spectroheliograph. Now it fits on a telescope, and down here is where it fits into the eyepiece holder of a telescope. And it's designed by a guy in France named Christian Buell, and it's something you build yourself. And Christian, he doesn't even like calling it a spectroheliograph. He said that's too much like a scientific instrument. He just calls it a fun tool for studying the sun, and it's definitely that. Now, didn't mean to show this, but I'm going to do a whole lot of background information before I really talk about what you can see with it. So I thought I'd throw in a few quick pictures here at the start, just to give you an idea of what I'm talking about when I say cool images of the sun.
First question.
Yes.
Did you take all the pictures in this presentation?
All the pictures of the sun, yes.
Okay.
But
What counts as small telescope?
80 millimeter. And I'll give you some examples coming up. You can use big ones too, but small ones work just great. Okay, I'm not going to talk about these pictures any. In fact, these are some early ones I took that aren't very good, so I made them very little, so you can't see any detail. But I'll show you some better pictures after I get through a boring set of background information. So the outline of the talk, I'm actually, first off, going to talk a little bit about the sun, specifically to tell you what parts of the sun you can see with a spectroheliograph like the Solex. Now, the way it works is based on spectroscopy. And so for anybody that doesn't know what that is, I've got a little one-pager on spectroscopy so you can see how it works. Then I'll get into actual mechanics of how a Solex builds an image, including both hardware and software. Got a one-page or so on how you build one of them. It shows some examples of ones people have built. And then I'll get to the images that I've taken with the device. There's a couple of things that are a little bit more advanced than just pretty pictures. I'll show those at the end. And then I've got some links if you're interested in building your own website you can go to and get more information. So starting off with the sun, this is a picture I stole from NASA. Shows a cross section of the sun. Of course, you're all probably familiar, but we have a nuclear reaction going on here in the core. Hydrogen is being fused into helium, produces a lot of heat, a lot of photons of light. Most of those travel through the radiative zone here. It takes like 50,000 years for it to cross that. It's the speed of light because it bounces around so much in a random walk. And then you reach the convection zone, which is a little bit interesting for the SOLEX. In the convection zone, the conditions are right so that hot material at the edge of the radiative zone will bubble up to the surface, cool off, and fall back down. And that motion gives rise to magnetic fields that poke through the surface of the sun and drives a lot of the phenomenon that we can photograph. Now, of course, you can't see any of that, because that's on the side of the sun. The first layer you can see is called the photosphere, and that is the bright, visible surface, if you will, of the sun. If you get your ISO certified eclipse glasses and put those on and look at the sun, what you're looking at is the photosphere. The magnetic fields coming through there cause some things like sunspots. That's one of the main phenomenon. But what the SOLEX is best for is what's outside of that. And that's kind of the atmosphere of the sun. The main layer is the chromosphere, which is about 2,000 kilometers thick, and it lies on top of the photosphere. It is a very rarefied gas, very low density, and so the magnetic field has a huge effect on it, and that's why there's so much interesting phenomenon to see in the photosphere, or chromosphere. Once you go outside that, there's a little transition, and then you hit the corona, which of course is all the charged particles streaming out of the sun, and they form the solar wind, and they'll look beautiful in a total eclipse. And I should mention, anything in white are things you can see with the SOLEX. Anything in black, you really can't. So the coronas, you can kind of see the inner corona a little bit with it, but not all that great. The last thing you can see are prominences, which are sort of like little flame-like structures off the surface. They start in the photosphere and go through the chromosphere up into the corona, and the SOLEX does a beautiful job at taking pictures of the prominences. The two main areas we want to look at are the photosphere and the chromosphere. Now, this picture is not with the SOLEX. This is a picture of the photosphere, and it's very easy to get a picture of the photosphere. You can get a solar filter, put on the front of your telescope, take a picture, you get something like this. This is with my 8-inch telescope and a Thousand Oaks optical solar film in front of it. You can see sunspots. That's the main thing you see on here. Very easy to do. So you don't really need a SOLEX for that.
Next question.
Sure.
Okay, you don't have to go back.
Okay.
That picture you just showed us, on the Thousand Oaks, was that taken with a monochrome camera with one of the Thousand Oaks orange filters? Or was that a color camera with the Thousand Oaks white filter?
That was a monochrome camera with a Thousand Oaks orange filter.
The orange filter.
That's all they had left whenever I was ordering before the eclipse.
Well, those are supposed to be the better ones anyway, right?
I kind of like the beta ones, but
Oh, okay. Oh, so you just went up with Thousand Oaks.
yeah, because I didn't have a big enough piece for my big telescope, so I had to order
Okay,
some more
so
material.
monochrome with the orange filter. Okay, got it.
So what we really want to look at with the SOLEX is the chromosphere. And there's a problem with that, though. The chromosphere is so rarefied, it's basically transparent. And right below it is the surface of the sun. And so you can't see anything in the photosphere normally. There are a couple of ways you can get around that, though. One of them is during a total solar eclipse, like we had back in April. And I took this picture with just a regular color digital camera stuck on a little telescope. And this is a picture just before we reached totality. So the moon's almost covered the sun, but the photosphere is still peeking through. The little bright spot there in the middle is diamond ring effect. But if you look to the left and right of that, you see these pinkish lines, and that's actually the chromosphere. In those areas, this moon has covered the photosphere, so the bright part's gone, and you can see the little pink stripe of the chromosphere. And that pink color is why they call it a chromosphere, because chromo means color. Now, the bad thing about this is you have to wait for a total eclipse, and this little strip that you can see is about 10 arc seconds thick, so it's hard to see any detail. Another way you can take pictures of the chromosphere, though, is in monochromatic light. And that's light of basically one wavelength, one color. And to understand why that's true, I need to give you a page on spectroscopy. So spectroscopy is, for anyone not familiar with it, it's just taking light from an object like the sun, using something like a prism and breaking it up into the constituent wavelengths, the constituent colors that make it up. And there's really three kinds of spectra. On the left, we have the sun. It's an incandescent object, very hot, very high density. And so it gives off what's called a continuous spectrum. So it gives all colors of the rainbow, nice smooth distribution, brightness versus wavelength is just a nice little smooth curve. Now ignore that one for a minute and all the light coming from the sun and look at this cloud of gas. Another way you can get a spectrum is if you excite atoms in that cloud of gas so that electrons around the atoms are jumping up to a higher energy level. When they fall back down, they'll give off a photon. It's at a very specific frequency due to quantum mechanics, and you get a spectrum that looks like this down here. This is the spectrum for hydrogen. This line's called hydrogen alpha, then we got hydrogen beta in the blue, gamma, delta, epsilon. So those spectra are very different looking. If you have like a neon light, that's the same phenomenon there. You have neon in a tube, put an electric current through it, and it gives off a bunch of little lines like this, and a lot of them are in red. Some neon signs are red. Other gases are used to get the other colors. Now, where it gets interesting is when you combine these two. You have incandescent light from the sun with its continuous spectrum. You shine it through gas, in this case, the chromosphere. And at these same wavelengths, the atoms will get excited, kick up those electrons. Well, that takes energy out of the sunlight. And so you get gaps in the spectrum, wherever those lines would have been. And that's the key to making something like a Solex work or any monochromatic light imager. You're going to take a picture just within that tiny little gap because there's no photosphere light to wash everything out. So suddenly it's not you don't have the big bright light behind you. Now these gaps are not just totally black. They have emission spectra coming from the gas in the chromosphere. And so way down in there, very dimly, you can get the light that shows you an image of the chromosphere, and that's what we'll be photographing. Now this is the sun spectrum, just an artificially generated one. We have ultraviolet up here in the upper left corner, infrared down here in the lower right. And each one of these little dark lines is an emission line from some element and some electron jumping from some electron shell down to another one. There's about 25,000 of these in the solar spectrum. I've labeled a few of them. This one down here is called hydrogen alpha. It's everybody's favorite. These three in the middle are due to magnesium. Those aren't as interesting, but I do have one kind of cool picture from that. Hydrogen beta is another one from hydrogen that's got a very interesting looking surface of the sun. Sodium has two lines. They're both boring. But right next to them is helium, which is odd because it doesn't really block the photosphere all that well. But with some different techniques, you can get a very cool picture with helium. And finally, in the corner, I got these two due to calcium. They both look alike. Doesn't matter which one you pick. A lot of people like that line too. And I'm going to show you examples of all those in a minute. So we want to get monochromatic light, stay in that one of those wavelengths right where there's an absorption line. How can you do that? First way, obvious way, is to use a filter. You can just stick that in front of your telescope and get all the pictures you want. It works. And these are 4 examples across the bottom. These 2 little telescopes are for hydrogen alpha light only. That's all they do. These other ones are filters that you can put on a regular telescope. Great thing is you can get excellent quality images with the filter. You can take pictures really quick, which is kind of important for the sun because the best time to photograph the sun is during the day. And during the day, the ground's heating up and you get heat waves and they blur your image. So if you take pictures really, really fast, every once in a while, you'll get a sharp image and software can pull those out. And they call that lucky imaging. And you can do that with a filter. Some disadvantages, they can be a little tedious to use because the area you have to stay within is very narrow range of wavelengths. And as the thing heats up, it can shift. And so you're always having to tune that filter to make sure you stay in the middle of the absorption line. And for a telescope like this one that I own, this $900 Coronado, they actually got for free. That's a long story. But it is a little bit clunky. And it took me a while till I got good at centering the lines where it's supposed to be. Biggest disadvantage of the filter is you can only use them at one wavelength. So like these fancy ones, they consider $5,000 to be an amateur, $136 to be a professional. This is a hydrogen alpha filter. Oh, now I want to do calcium K. Well, you buy another filter. You write another check. Oh, I want to do magnesium. You write another check. So that's an expensive way to do it. The second way is, of course, the way we're going to be talking about is with a spectroheliograph. Now, it's got disadvantages. It's harder to get a quality image. You're going to see it's a complicated procedure for getting a picture. I hinted at that on the safety page because that picture looked nothing like the sun, and you have to do some work to get it to look right. Also, you get a low frame rate, so lucky imaging is right out. It takes me at best 6 seconds to get a picture. Most of them take about 20 seconds. It's even more tedious. I try to do astrophotography. I'm lousy at focusing. That's the big thing that drives me nuts. This thing has essentially 3 focusers on it. So you can imagine how much hair you pull out working with it.
Okay.
Sure.
How do you know which one's out of focus if you got 3 focusers?
Well, each one focuses a different thing. 2 of them focus the spectrum itself. One of them focuses the sun.
Okay, yeah,
And there's techniques you can use to figure out which one's out of focus.
okay, I believe that.
Now, the great thing about a spectroheliograph is you can use it at any wavelength your camera is sensitive to. It's got a knob on it. You turn it. I want hydrogen alpha. You turn it over there, hydrogen alpha. I want calcium H. Turn the knob over that way, and you can see it. The only problem is you've got 25,000 little lines, and you have to figure out which one's the one you want. But you get better at that after a little while. The other good thing is that it's relatively cheap compared to those other options with the filters. You can build a Solex for $600 pretty easily. You can do it a little bit less than that. You do have to add a scope and a camera, but as you'll see, a very cheap scope works. And the camera, probably about $300. You really want a monochrome astronomy camera to do this. No, because your exposure is going to be very short. And one other advantage of it is you have a very narrow bandwidth. That is how many frequencies are in your image. How narrow of a band can you look at? And this is an example trying to show that. I've got brightness versus wavelength, and this is right around that hydrogen alpha line where this, hydrogen alpha is absorbing the light from the photosphere here, so it's dark. And right down in the bottom here is where the chromosphere light is living. So you want to only look at light in that little narrow dip. And this shows 4 different types of telescopes and filters. The Solex does the best. It's much, much smaller than the width of the hydrogen alpha line, so it's very easy to ignore all the photosphere with it. That $36,000 filter is only about half as good. Its bandwidth is twice as big, which is kind of funny. The $900 one, like I've got, it's 1 angstrom wide. It's about as wide as hydrogen alpha line. That's one reason it's fiddly. You have to keep it perfectly centered or else you get photosphere light messing you up. And then if you're a deep sky photographer, you may have a hydrogen alpha filter and you're like, I'll use that for the sun. It doesn't work. First off, there's too much light. It'll probably crack. And also its bandwidth is huge compared to what we're doing here. 2 nanometers would be a very expensive deep sky filter. And that's all you're getting is just about photosphere. The picture will look like you just used a white light filter and that's all. So finally, that out of the way, how does the Solex work? Or any spectroheliograph for that matter. This is a little cartoon I made, kind of a cross-section of a Solex. The thick white lines, like this line is the case, and these lines, these are tubes that hold the optics. Another tube comes up here. We have a camera mounted here, and that's the red outline. And the camera sensor is this little red line in this circle. Now this mounts on a telescope right here. The telescope's pointing to the left, and the sun's 93 million miles that way. And what you've got is, I've tried to do some ray tracing here, some very crude ray tracing. And so I also show 3 rays of sunlight coming in to the system. Now, right here's where they reach focus. If you were, this is a regular telescope taking a picture of the moon, you'd put your camera there and you get a nice picture of the moon. For the Solex, you don't put a camera there, you put this slit. And that's a piece of glass that's coated with an aluminum coating that's totally impervious to light, except for a very, very narrow slit down the middle of it. It's only 10 microns wide, which is 10 millionths of a meter, about as wide as the pixels on your camera, roughly. So instead of getting the entire image of the sun coming through, you only get a picture of a slice of the sun, a very, very narrow slice. Now that goes past focus, hits this collimator lens, all light goes parallel, and then it hits a diffraction grating. A diffraction grating is another way that you can break sunlight or any light up into a spectrum. It's just a piece of glass with a whole bunch of little lines on it. In this case, 2,400 lines per millimeter. Now, each of these rays hits, breaks up into a spectrum, comes off at this crazy angle, and some of that light hits this objective lens and gets focused on our camera sensor back here. In this case, only the yellow light is hitting the sensor. I've gone on and drawn in the other colors, even though they can never actually get there because the tube's in the way, but just to show you where the spectrum is, red end, the violet end. And so we'll be taking a picture of a tiny piece of the sun spectrum in the yellow part of the spectrum. If you want to take a picture of hydrogen alpha down here in the red, you just rotate this grating a little bit, that slide the whole spectrum up until red was on the sensor. Okay, so now you got a picture of a piece of the spectrum. That's still not a picture of the sun. So now we need to introduce some software. Now what we're seeing here is just a white light image of the sun. This is what your telescope is looking at. And this red line corresponds to where the slit is. So really the only thing going through the Solex is the light in this little tiny red sliver. That gets broken up into the spectrum, and this is what the camera is taking a picture of. This is a hydrogen alpha line. There's a bunch of other absorption lines. I have no clue what those are. And in this case, I've actually got it lined up on a sunspot. So the sunspot has this little spectrum in there. And what we want to do is only use the light from this that's in the hydrogen alpha line. So there's free software that comes with the Solex. It takes this, it finds the darkest line, interpolates from the center, and gives you one column of data for your final picture in hydrogen alpha light.
I got a question.
Sure.
Okay, I'm not understanding this.
Okay, sorry.
Okay, so Phil,
Mhm.
first off, how are you gonna sweep this thing across the sun?
That's what I'm about to tell you.
Okay, tell me.
Okay. You know, the thing is, one slice of the sun is not what you want. You want a whole bunch of slices together.
Yeah, I got that. But how do you-
So what you do is you point the telescope so the slit is over here to the left of the sun, and you start recording a video. And you try to do it at very high frame rates. In fact, you crop around the hydrogen alpha line to get as little as possible so you can get the frame up to about 150 frames a second. That's what you shoot for. Then when it's running like that, use the slow motion controls on your mount, and you sweep it across the sun at the proper rate. When you get to the end, off the side, you stop the video, and now you've got a movie of about 3,000 frames that look like this.
Okay, got it.
Yeah, the software extracts a slice from each one, stacks them together, and you get a picture like this over on the side of the sun in hydrogen alpha light.
All right, that's question number one.
Okay.
Okay, number two, the only two questions.
Nope.
Okay, on your spectrum right there, where is the column? Is it the dark line? Is that? column?
It's in the middle of the dark line.
Okay, but in your dark line, I don't see any variation.
There is. It's just because of the exposure I've used here. There are variations in brightness. The variations in the chromosphere are a lot less than the variations in the photosphere. And this exposure, I didn't want it all to be washed out where you couldn't see the other lines. You normally use a bit longer exposure,
Okay,
so you're seeing detail in that
okay,
line.
so it really is just that line is the column, that dark line in the middle. Is
That's
the
right.
column.
And it's actually the center of that dark line. It's not the
Center of
whole
that
width.
dark line is the column at that moment, and that's what you're storing.
That location on the sun.
I got it. I looked at your presentations and I couldn't figure this
Yeah.
out.
Yeah. As you stack all those together, you get a picture of the sun.
Got it.
I'm only showing it up to the red line. Of course, you go all the way across the sun. to get the whole thing. Okay, so that's how Solex works. And you're saying, wow, I got to have one of these. So what's involved? Maybe not. So what's involved in building it? Well, first off, you have to have the case and all the parts that hold the optics. And those are all 3D printed. They're made out of plastic, which is a little odd having something looking at the sun that's made out of plastic, but it works quite well. If you have a 3D printer, you go to Christian's website. He's got the STL files. You download them for free, print them in black PETG. You've got a case.
Say that again, black what?
PETG. It's a type of plastic.
You got, right, but you got to use that instead of PLA, right?
You don't have to, but he recommends PETG just because it takes the heat a little bit better.
No kidding. Okay, so I made something out of PLA, and the first time I took it out in the sun, it warped. It was ruined it.
Right.
So you're using PETG plastic and not PLA
That's right.
on this thing.
That's right.
Okay.
And you could use ABS if you wanted to or whatever,
Right.
but PLA is not the best.
Yes.
And if you don't have a 3D printer, you don't know what any of this means, it's no problem. You go to his website, grab this zip file of all those files, and you send it off to a company on the internet, and they'll print one for you and mail you the plastic parts. You have a question? Well, at the very end, I'll have his website, and it's got links to all kinds of stuff. It'll be on the last page. And so they'll give you all the parts. You then have to have some screws to hold it together, and something called heat set inserts, which are like little nuts that you heat up and melt into the plastic so the screws have somewhere to bite. And so that gives you the case. Now you need optics, and that's the expensive part. Christian's worked with a company called Cheliac in France, and they've built an optical kit specifically for the Solex. It's got the two lenses you need, that precision 10 micron slit, and your diffraction grating. And all these parts fit perfectly in the 3D printed parts up here. Once you have that, the only part left in the Solex is a helical focuser. He recommends just using a commercial focuser. That goes between the camera and the Solex. You have to focus that a lot, and it's better to use a nice metal part instead of a plastic part for that one thing. Now, once you have the Solex, you still aren't done. You have to have a telescope and a mount, and I'll show you examples in a minute. And then the monochrome camera, and you need a neutral density filter to go in the front of your telescope. The problem is if you don't do that, the light will damage your slit. It'll destroy it.
Okay. So neutral density, what kind of neutral density though? It's not like a white light solar filter, right? It's
Right, it's like it's used for photography
a
normally.
true neutral density.
Yeah, it's like an ND8 or ND16 or something. It cuts the light down by like a factor of 8 or
Yeah.
16.
But the sun, there's no issue with the sun going through the neutral density filter?
No, the filter is just fine, and then it gets the heat down enough that the slit doesn't destroy itself.
Okay,
It's not nearly enough to look through. That's like 100,000 or something.
right, okay.
All right, so the next slide just shows what the finished product looks like. Over here is where it mounts to the telescope. The slit is in this collimator block that slides back and forth. That's one of the things you have to focus. This dial is attached to the diffraction grating. That's what you turn to pick your wavelength. Here's that helical focuser. It's about $60. And then there's your camera up there. Now, the cool thing is, since it's plastic and 3D printed, especially if you have a 3D printer, you can modify this thing all over the place. If you don't like the way something works, change it. And so a bunch of people have sent Christian pictures of the Solexes that they've built. Of course, it's plastic. You can pick any color you want. Black is good, though, for the optical parts. But people have made changes like here they've replaced that helical focuser with a plastic one. This guy's used the same thing. These guys have a different designs. That saves you $60. The one in the middle is mine. I got tired of that plastic collimator block because even you only have to focus it once in theory. I'd have to twiddle with stuff, and it drove me insane. So I replaced it with just another helical focuser. Also added a little focal drawing and a little thing to help me find the wavelength. But that's the fun thing about it, just tweaking it to make it work better for you. Now, I keep promising that I'm going to show you the camera and mount you can use. Here's a few examples, most of them from his website. So these are not pictures I took. Here he's just using a 200 millimeter camera lens. So that's pretty, if you got one of those, it's basically free for your telescope. And he's piggybacking it on a Newtonian. It's on an equatorial mount. Equatorial mount's the easiest. If you have like a go-to mount that you can speed up and slow down, that's the best thing to use. But you can use a lot of different things, as you'll see. Another thing that Christian likes is this plastic Maxitov telescope you can get on Amazon for $130. It takes surprisingly good pictures, and he likes it because it's plastic and the Solex is plastic, and it's like, that's just the way it should be.
It's probably star blue, something like that, sort of blue.
Something like that.
Yeah.
They have several different models with different little cheap accessories with it. This is what I use most of the time. It's called a Orion Sharp Tube 80. Unfortunately, you can't get Orion Sharp Tube 80s anymore, but you can get them from a different manufacturer. Mine was $110. So it's a pretty cheap telescope. You can see my little neutral density filter attached on the front. I 3D printed a little thing to hold it. This is something I tried and I haven't been successful yet. This is a 6-inch Newtonian that I bought in 1980, my first real telescope. And the reason I'm showing it is because it's just got a regular clock drive. You can't speed it up, you can't slow it down, so you can't sweep it across the sun to make the spectroheliograph work. What you do is you get the slit in front of the sun, and then you plug the mount. It stops, and the Earth moves the slit across the sun. It takes about 2 minutes to take a picture, but it works pretty well. And if your mount vibrates, in the motor or something, well, this eliminates that problem. Because of the vibrations, all your pictures look like Charlie Brown's shirt. They just have these little jaggies all over them. And I've taken a lot of those pictures. Now, you don't have to go cheapy. This is another one of Christian scopes. It's a $7,000 Takahashi. He takes some spectacular pictures with that. But the final one is just something he had was a refractor on a regular photographic tripod. You want a pretty solid one, but you use the same technique I use with the Newtonian. Get it in front of the sun and let the Earth do the work for you. So finally, all the background stuff's out of the way. We can start looking at some pictures from the Solex. And I'm going to start with a very boring picture. This is a picture of the photosphere, which I said we really want the chromosphere, but you can also take pictures of the photosphere. All you're doing is, instead of picking a wavelength that's in one of those absorption lines, you pick one that's not in an absorption line, some of the bright light from the photosphere. And they're still interesting. Sunspots show up really well in photosphere images. You can also see this maybe very faintly. Oh yeah, the little white areas around here, these are called faculae. They're areas of fairly high magnetic fields, just not nearly as high as sunspots are. Another thing that you're supposed to be able to see is called granulation, which are these little convection cells coming up to the surface of the sun. They're about the size of Texas, which is like 2 arc seconds at this distance. Unfortunately, an 80 millimeter telescope on a hot sunny day is not conducive to taking pictures of something that small. So I've never got a picture of granulation. The final thing is limb darkening. That's a characteristic of the photosphere. It looks darker at the edge than in the middle. The sun's really the same brightness everywhere. It's just the photosphere is about 500 kilometers thick. At the bottom, it's 6,500 Kelvin. The top is like 4,800 Kelvin. So if you look right in the middle, you're seeing all the way down to the really hot layer, and it's bright. Over here, you're only seeing the top layers, which are cooler and darker. So that makes it look like, this is a better place to spend summer kind of a thing.
Sorry, what was the thickness again?
500 kilometers roughly. So finally, we'll get to a chromosphere picture. This is one that I took in magnesium, one of those 3 magnesium lines. It's actually the right-hand line, the 3 I showed earlier. And the first thing I should mention is this weird nomenclature. Mg is magnesium. The Roman numeral 1 means it's got all of its electrons. It's a neutral atom. Magnesium has 12 protons, so that means you've got 12 electrons for what it's worth. B1 is an arbitrary designator. Fraunhofer, who was the first person that really investigated these absorption spectra, he came up with this numbering. But this is in the green part of the spectrum, and so I've colored this picture green. The software will do that for you automatically, and I really like green, so I colored these. Plus, if you're really bored at this point, you can at least say, wow, that's a pretty green picture of the sun. Now, the thing is, magnesium, the temperature and everything is right for magnesium to absorb and then re-emit light from the photosphere at a location in the solar atmosphere that's very close to the photosphere. So this picture looks a whole lot like the previous one. You're seeing the same faculae, although you're seeing them a whole lot better now. And that's just, I think, because the narrow green light is giving you a lot higher contrast.
Okay, and you said the software. What is the software again?
The software that extracts the line of data and creates the image. Yeah, it creates the image and then it colors it. You can color it by the wavelength. This particular one, 5100 angstroms, is a green color and it'll make the image green.
But what is the software? What's it called? What's the software package?
One that Christian wrote is called INTI, I-N-T-I, and it's linked on his website.
Okay, so you get it on his website?
Yeah. I use another one called JSOLEX that somebody else wrote because it runs under Linux, and I normally use Linux. And all these are done with JSOLEX.
Okay.
And there's a third one I can't remember the name of. They're all free. And so there's magnesium. Now, if we go a little higher into the chromosphere, though, we get more interesting things happening. This is a picture in hydrogen alpha, hydrogen beta wavelength that not too many people look at. I don't know why, because it's very cool looking. Whole lot of detail going on. It's kind of a cyan light that we're using. And it's still pretty low in the chromosphere, only 100 to 400 kilometers above the photosphere, but shows a lot of detail. One thing you'll notice is there really aren't very many sunspots. A little one visible here and some very tiny ones if you know where to look over here. That's mainly because this magnetic field is really strong in the photosphere, and once you get in the chromosphere, it starts spreading out and doing all kinds of cool things like making big patches like this. And so you don't really see them as sunspots anymore. I'm not 100% sure what all the fine detail here is. I think it's something called the chromospheric network, which I'll talk about in a few minutes when I talk about calcium. Nobody discusses hydrogen beta, so I've had a very hard time finding out what we're really looking at. One thing I do know is these lines here are called filaments, and I'll show it that better in the next page, which is for hydrogen alpha, which is everybody's favorite line. Here's my hydrogen alpha image. Now this one I didn't color because the color tends to mask very fine details, and this picture has a whole lot of detail, and so I didn't want to hide any of it. The hydrogen alpha line is produced about 1,500 kilometers up into the chromosphere. So it's about 3/4 of the way through it. And it's the best wavelength for looking at those filaments and also prominences and filiproms. Although you can barely see some tiny prominences at the edge here. I'll show better ones in a second. You can also see kind of an interesting thing, a light colored area underneath the filament. And some of that's caused by the filament reflecting light back down to the sun and raising the temperature. Thought that was kind of neat. But up here is the really detailed part I wanted to show you. And you see a whole bunch of little lines, look like little worms. In fact, they look sort of like metal filings on a magnet. You know how you put those down to see magnetic fields. And they follow magnetic field lines. They're actually little tubes, magnetic flux tubes that line up at the local magnetic field. And they show up pretty well in hydrogen alpha. Okay, so I've shown you filaments. The next page shows you prominences. And I brightened this picture a little bit and also did the coloring bit. But here's some prominence over here. That's just material suspended above the sun's surface held by the magnetic field. These are called hedgerow prominences. This one's kind of an arch prominence. And those are pretty cool things to see on the sun. On this one, we've got a philoprom, which is down in the corner. And basically all it is, it starts out as a filament, and then when it's in front of space, it's a prominence, because those two things are the same thing. And so if you get a long one that goes across the edge, they say, well, we'll call that a philoprom. They stick the two words together. There's really nothing magical. They're all the same phenomenon. Now, one thing, when I was taking this picture, I was trying to take a bunch of images so I could stack them, reduce the amount of noise, get more detail. And something cool happened, though, on the sun when I was doing that, and that's the next sequence. Here I'm just looking at the eastern edge of the sun, and you'll see this bright spot that grows up to a pretty good size. This is much bigger than the Earth, this little white dot here. And for these first 6 pictures only span 2 minutes. I was taking pictures every 23 seconds. That's the way it worked out. And this is probably related to a solar flare. There's something called a surge where it can throw material off the sun. And by scaling up the picture, I found that its peak height here was about 11,000 miles, or it's 8,000 miles across. So these things are pretty big. And it climbed at about 50 miles a second. And then about 3.5 minutes, it reached its full height. So even though the Solex can't take pictures fast enough for lucky imaging, it does. You can still see some fairly interesting short-term phenomenon. Okay, my next to the last pretty picture is one of the calcium lines. This is called calcium H. The 2 means we're missing an electron on our calcium atoms. This is actually slightly in the ultraviolet. It's just before 4,000 angstroms, if you want to call that the cutoff. The calcium lines produce at a bunch of different altitudes, but most of what we're seeing here is fairly low, around 400 kilometers. Now, these white things look like a cracked eggshell all over it. That's the chromospheric network, which are caused by something called supergranules down in the photosphere. It's areas where you have these fairly large convection cells, and it's really bright around the edge of where those convection cells are. So they last pretty long time, but those are fairly interesting. Other thing that calcium is famous for are these regions called plague regions, these very bright lines. Those are sort of like the faculae that I showed you for the photosphere, except no one's really sure how the two are related. They're pretty sure they're related. They don't really know how. But if you want to see the chromospheric network and plague regions, those are calcium is the place for it. The last picture is a weird one. And this is that weird helium line that doesn't really block the photosphere. It's created a different way. It doesn't take photospheric light and reprocess it. Well, it does, but before it does that, ultraviolet radiation comes down from the corona and excites the helium and makes it fluoresce, makes it emit light. And unfortunately, it only makes it about 3% brighter than the photosphere. So it's hard to see. And to make this picture, I took a picture at the helium wavelength and a continuum picture like the very first one I showed you, and you subtract them so you can see those subtle differences. The outer edge, this bright edge, that is the emission coming from helium due to the corona. And it looks really bright here because there's no photosphere behind it to subtract. So you see it in its full brightness. In the middle here, a different phenomenon is happening. These dark regions are actually the plague regions that I showed you on the previous picture that were really bright white. And I don't know the process. I haven't been able to find that yet. But those do something with electrons that interact with the helium in the chromosphere, and the helium absorbs that light very well. And you end up, wherever these plages are, you get this black area with lots of detail. I was surprised with the amount of detail I could get. You can also faintly see the chromospheric network here. Now, so those are just pretty pictures. The Solex, though, has that very narrow bandwidth, and that lets you do a few other things that are kind of cool. The first one is you can create something called a Dopplergram, and the software also creates these automatically. You know, what happens here is you've got your hydrogen, it's absorbed some light from the photosphere, and it spits some more back out because it's just a hydrogen alpha image. But if the hydrogen's moving, like if it's moving away from you, it's going to be redshifted a little bit if its velocity is high enough. And so that location of that emission line will be slightly shifted towards the red. If the gas is moving towards you, it's going to be shifted towards the blue. And so the software, if you wanted to make one of these, instead of giving you the data right down the middle of that dark absorption line, it gives you a line, one picture with the line like 3 pixels to the blue, one picture with the line, you're going 3 pixels into the red from the center. If that makes sense. You look confused. And And this is a result when you combine those together. The first thing you notice is the left half of the sun is blue, the right half is red, and that's because the sun is rotating on its axis and the left side is coming towards us, the right side is going away from us, so they're blue and red shifted. It's a very subtle difference because these are not relativistic speeds, but the Solex is sensitive enough to barely see that change due to the velocity of the gas. My last picture is called a magnetogram. It also exploits that narrow bandwidth. And this is actually a picture of the magnetic fields in the photosphere of the sun. And the way you can see a magnetic field is through something called the Zeeman effect. Whenever, in this case, it's iron, this line I'm looking at is an iron line. Whenever the iron electrons are being kicked up to higher levels and falling back down, if that happens in a strong magnetic field, then that absorption line we've been looking at gets split into multiple absorption lines. And the stronger the field is, the farther apart they get separated. And so by doing something similar to Doppler, where the thing makes two pictures, one just to the left of the center, one just to the right, and then doing some stuff with some polarizing filters. You'll have to check out Christian's site to understand all that. But doing all that, you get a picture like the one on the left, which I took. Ignore these diagonal stripes. Those are Newton's rings, just an optical effect I couldn't get rid of. What you really want to look at is the black and white areas. Well, first off, the gray areas, that's where the magnetic field is too weak to really see. The white areas are where magnetic field lines are strong and they're coming out of the sun, sort of like the North Pole of a magnet. The black areas is where the fields are going back into the sun. It's like the South Pole of a magnet. And so what we're seeing are these magnetic dipoles on the sun. The picture on the right is not with the Solex, it's with the SOHO solar observing satellite that's in orbit around the L1 point between the Earth and the sun, about 1 million miles from Earth. And they use a similar technique to measure the magnetic fields. And so I'm comparing how good does my plastic Solex do against this satellite. And it does fairly well.
Okay, hold on.
Sure.
You're not gonna get away that easy. Okay, so where do you put the polarizer in the middle of all this?
You put it just in front of the slit. Because what happens with the Zeeman effect, depending on the north or south pole, the
Right.
polarity of the stuff, it also circularly polarizes the light.
Okay,
And depending if it's north pole maybe is right circular polarized and south is left or vice versa. And so you have two filters, one that's a right circular polarized, one left circularized. And so that separates out the lines and you can tell, oh, this was a north area, that's a south area. And when you do the math inside the software,
did you take two pictures then, one
Yep.
left and one right?
Yep.
So you took one left and one right, and then you're telling me there's also a wavelength shift also or not?
there's a wavelength shift. It's got the polarization that
Right.
lets you see the wavelength shift on one side or the other, depending on the sign. And then the amount that it shifted over
Okay.
tells you the strength.
So you're polarized, it's not a linear polarized, it's a circular?
Circular
polarized?
polarizer.
An optical circular polarizer.
Mhm.
You got left one and the right one.
Right. In fact, what Christian uses is he says, they give you the free 3D glasses at the theater, which I think you're supposed to leave there, but he takes them and cuts them up and sticks them in. I actually bought some little fancier material off Amazon and made my filters from
I
that.
thought those were linear polarized.
No,
Circular?
they're circular.
Oh, I didn't know that. Okay.
I didn't either, but until I did
I
this.
assume they're linear, but they're circular.
Yeah.
Okay, good.
So, but what I was wanting to do here comparing to Soho, I've got this little ladder-like structure, which they have, the big white spot. I've got the same basic structures they do, just my blacks aren't as black and my whites aren't as white. I got this little cool thing with a dot in the middle, they've got that. And so I thought it was very cool. I can take my plastic $400 thing on an 80 millimeter telescope in my backyard in Clear Lake shores and get a picture that's at least a little bit like Soho. And I can measure the magnetic fields on the sun. And so that's really everything I've got. These are the links I was talking about. The first one is the main Solex website, and it's got a lot more information, background on how it all works and the different kinds of pictures you can take and how to build the thing in more detail. And if you don't get this address down, just look for Solex and SHG. SHG stands for spectroheliograph, and it'll be the first link that comes up in Google. If you leave off SHG, there's a lot of companies that call themselves Solex, and it won't be the first one. Second one, he has a YouTube channel. It's all in French, so you have to turn on the YouTube. If you don't speak French, turn on the YouTube auto captioning, which is hilarious. You can understand about 80% of what he's talking about. But he mainly just shows how to build the thing and how to calibrate it and that sort of stuff. And finally, there's a IO group that's also in French mostly, although you can post in English and people will respond in English and sometimes in both languages. And it's very useful if you actually start building one of these things and doing things with it. And the final two things, I bought several books trying to understand the sun. I still don't understand it at all. Probably everything I've said about the sun's been wrong so far. But two books I found very useful. The first one is this Pocket Guide by Jenkins. And the main thing that's good in it is chapter 2. It describes all this stuff that you can take pictures of on the sun in very nice detail. It explains it better than any other book I've really seen. The bottom of those is my favorite book, Solar Astronomy by Valedric. It's a French book. You have to order it from the publisher for 69 euros, free shipping to the US. It is about an inch thick, paperback, large format. It's got beautiful pictures of all kinds of phenomenon on the sun and explanation of where they come from. Some are from spectroheliographs, some are from filters, and all of them are just very amazing photographs. So I highly recommend that book. So that's what I've got. That's my solar adventure. And does anybody have any
Yeah,
questions?
one more.
Sure.
Okay, so when you had your dial calibrated to the different wavelengths, right?
Mhm.
So when you
Pretty close.
Huh?
Pretty close.
Yeah, so when you're calibrating your dial and making sure, how do you know you're actually at the right?
You have, there's pictures sort of like that when I showed the whole solar spectrum. There's some that are much more detailed than that. And you know roughly where it is. You turn the dial over that area and you start looking at the little lines and say, no, this isn't it. And you just keep going until you find, like hydrogen alpha is a very dark
That's
line.
gonna be a big one.
It's like, oh, that one's easy. You figure out which one it is. You make a little mark where that is on the dial. And then you do some other lines like that.
But you're not looking, you're looking at the camera, is that right? You on the camera?
Right. Just a still image off the camera because you're seeing that piece of the spectrum wherever the thing is rotated to.
Okay, I guess some of them are built this so they make it easier to, like a hydrogen, the calcium H and calcium K are near each other, so that makes those easy to find.
Yeah, those both show up at the same time on the camera.
Right, okay.
And some of the ones like hydrogen beta is hard to find because it's not all that dark and there's a lot of dark lines around there.
Yeah.
I usually stumble around a little bit. You take a picture and it's like, oh no, that's a continuum kind of thing. Because a lot of those lines are produced in the photosphere, actually. Most of them really are. And so they all give you the same picture.
Good question.
Sure.
So,
Hi, Chris. Here you are.
So incredible pictures. You said this was all with the short tube 80, so that's like an F5.
Some of them were, other ones were with my Zenith Star 73, which is an F5.9, I think. I could see a little bit bigger picture. I couldn't tell you which ones were which.
Is it, I mean, I'm kind of old school and did the Daystar stuff and tried to get to the magic number of F30, right?
Right.
So that's kind of when I was playing around with some stuff. But does this work better on longer or shorter waves?
The optics are supposed to be optimized for about F7 to F10.
Okay.
That's the sweet spot for it. It doesn't make much difference if you go a little bit outside of it. I don't know if you noticed, but my calcium image was a little bit fuzzy. And I think that's because I'm doing just F5. Sometimes you get a sharper image if you stop it down a little bit to get in that F7 to F10 range. But it doesn't seem all that sensitive.
Well, this is a game changer. This is like incredible.
Oh, yeah.
Dial in everything rather than just stuck in hydrogen alpha, right?
Right.
Go wherever you want.
And of course, the picture, if you get a lot of lines in there, you can get multiple pictures at once. I mean, the software, you can tell it, don't give me the center of it, give me 84 pixels that way. That's what you have to do for helium because you can't even see it. You can put it on the limb where it emits light and you can see the bright line. You say, well, that's 87.2 pixels away. And so you say, go 87.2 pixels from sodium and it'll find it for you.
What resolution camera are you using?
This one is, I'm using a ZWO ASI 183. The pixels are 2.4 micron, I believe, and it's about 3,000 pixels tall. So about 4,000 pixels wide, I guess. I don't remember the exact number.
So in this, we would want ideally the smallest pixel possible.
Somewhere around 2.4 is where you're getting all the resolutions you can get out of it. That's what he kind of recommends. The 183 is a bigger camera. They also make one something else that's the same pixel size but smaller. Yeah.
So can you measure the size of sunspots with this?
Can you do you could because you can see the sunspots in the image, I guess you scale off the size of the sun. I don't know how you normally figure out what the sizes are in a nice scientific way.
Yeah, I was thinking about the accuracy level, like, that, I mean, of course, even with the naked eye, you can see different sizes.
Right.
But is it good enough measurement that you can kind of get the rough estimate of the size?
You could. Now, one thing that's going to be a little bit of a problem is if you're sweeping across the sun, it's highly unlikely you're sweeping at the exact speed that's going to give you a round sun. You always get these footballs. So you try to go a little bit slower than you have to so that you get all the resolution you can. The software automatically then goes and makes it round. And there's a chance it doesn't make it just perfectly round when it does that. So if you're trying to do something very, very accurate, it's probably not the best way to do it. But you can get something very close, I would think. I haven't tried that. But anything else?
Okay, one more.
Mm-hmm.
Okay, so my understanding is, there's all these lines in the solar spectrum.
Right.
My understanding is we don't know what all those lines correlate to.
I think we know what almost all of them do, if not all of them.
Are you sure
I
about that?
don't.
Yeah, but are you sure that's true?
I bet it is, because I mean, there's some of them, like you,
No betting, you know that's true.
I don't know that's true.
No, because really, no, I believe, look, there are many lines in the solar spectrum, we don't know what they are.
Okay. One reason I think that we probably do know what most of them are is like you can take a corona image, the very inner corona. They're awful looking images. That's why I say you really can't do it. But they use iron 14. So it's iron that has 13 electrons stripped off of it. And so if you can get something as esoteric as that, I think they have a pretty good idea what the other ones are that are not so crazy.
I've heard this as an argument that we don't know what all the elements are. Because they say that because the solar spectrum, there's lines in solar spectrum, we don't know what element they correspond to, which is a reason people think there's elements that we don't know what they are. You ever heard that one?
I have not heard that one.
Okay.
Really? The periodic table of elements could be expanded even broader?
Yeah, that's my understanding, is that the lines of solar spectrum, there are ones in there that we don't know what they correspond to.
I mean, most of it is just because you have more neutrons than, basically, like hydrogen has two other isotopes, yeah.
Right.
So you have a field of isotopes throughout.
I
So a
understand,
lot of that could be because of that.
I understand that, but I think even with that in account, I think there's ones they don't know what they are.
I'm sure they got grad students that are trying to
I've seen
figure it
an
out.
argument several times that that's the argument that there are elements we don't know.
Well, I have to go and try every one of them and see if it.
Why have you?
Well, I don't think there's any elements in between the ones we know about.
That's pretty good guess.
That's how you just call it Hollandian.
There we go.
Anything else?
Just one more.
Yeah.
One more on the technology. Other than the neutral density filter that you had in the past, is there any other need for energy rejection filters or anything like
No.
that? Or you just like, because the slit is.
Yeah, the slit gets rid of a lot of it and
Yeah,
reflects a lot since it's so reflective. But and most of them are just 1/8 or 1/16, and it seems to work quite well. He's got a little rule of thumb, or rule of hand. You stick your hand back at the focus of the scope, and if you can hold it there for like 20 or 30 seconds, then the slit's probably gonna be okay. That's what Christian
One
does.
of the pictures was that big Takahashi telescope, right?
Mhm.
And
Yeah, it's 128 millimeter, I think.
You don't need to dim that down in any way with any energy rejection filter?
No, in fact, my Newtonian's 6-inch, and it worked just fine. I had to go to a little bit darker neutral density filter, I think, with it than I did on my little 80 millimeter, but it didn't have any problems. Just hold your hand back there and make sure it doesn't get too hot before you destroy your $100 slit. All right.
Any questions for Phil?
Okay, that was a cool presentation. All right, Ron's not here tonight with the DVD library, so we don't need to talk about that. Okay, the meeting after the meeting, when we get done here, we're all going to Zoom up to Mod Pizza and have the meeting after the meeting. It's the one you You shoot up Middlebrook, take a left on Clear Lake City Boulevard, and right in front of HEB is Mod Pizza. We'll get together and eat pizza and talk about astronomy and other really. Oh, there they are, the king and queen of Mod Pizza. There they are. Didn't even see you guys. See, this is really hilarious because we've been going to this Mod Pizza forever. I don't know. And these younger people, I'll call them, looked at us and they thought we were kind of odd, but they thought they kind of liked us because there's something seemed like they were kind of odd. So now they've taken an interest in astronomy because we keep going to Mod Pizza, and there they are. There's proof there. So, okay, I'm glad to see you guys. All right, that's right. Okay, so we'll go to Mod Pizza afterwards, and that's that. Okay, so we're going to take a short break for 10 minutes, and then we're going to get back here for the second half of our meeting. See you then. Okay, we're ready to get started for the second half of our meeting. We're getting started with the second half of our meeting. This thing is not working. Hi, Rick. We're getting started with the second half of our meeting.
Does that mean we're starting?
We're getting started with the second half of our meeting.
That's very nice.
Yeah,
Buy
this.
that or make that?
No, I did not. Are you kidding me? No, I did not make this. This thing is called a rungu. It's from Kenya. And somebody gave this to me a few weeks ago, and they told me that you're supposed to use this when you're trying to get the attention in a meeting. Like the chief would come in, and you take this thing, there's these little things on here, and you do this back and forth. It's supposed to make everybody sit down and pay attention. It didn't work.
But you have to dance though,
What?
holding that and dancing.
I'm not doing any dancing here. So this is a rungu from
Yeah.
Kenya, and I'm going to report back that it only partially worked. It did not work on Rick or David. It worked on everybody else.
Hey, I'm sitting down.
Yeah, I think
We were looking at it.
I think it's actually a club where you go hit them with it once you can't get their attention. Okay, all right, very good. So welcome to the second part of our meeting. Next up, we're going to have two good presentations tonight. We have Paul Lotz, who's going to tell us about my early adventures with C-Star S50. And this may sound familiar to you because where's Reed? There's Reed. Reed's got one of these things too. And so does Ken Lester. And I think there may be some other people in our club that have the same telescopes. This has been very interesting that people are all buying the same thing. And now Paul's going to tell us about his experience with one of these things. So let's welcome Paul.
All right, so forward is enter and to go back
Yeah,
is
enter is forward. You want me to show you?
sure.
And then, okay. This is not the way it normally is. Okay, yeah, I can just hit enter to go forward. And then if you want to back up, there's a backup
okay,
back
okay.
down there.
All right.
And you can use this to point at stuff.
Okay.
All right,
Thank you.
very good.
All right. All right. So thanks for the opportunity to come and speak. So I will use the enter key. Okay. This is the C-Star S50, and I put some of the specifications here. Reed already covered all the details in June, so I didn't repeat everything. But bottom line is it's an apochromatic 50 millimeter refractor, f5, and it pretty much does everything. You tell it where you want to go. You connect to it with an app that you can use on your cell phone, or I highly recommend using a tablet because it's bigger and you can see a lot. It's just cooler. But the bottom line is you tell it where to go, and you can autofocus, and then it uses a plate solver to figure out where it's pointing, and then you tell it to take an image. And it has a couple of built-in filters. One is just a light pollution filter, but the other one is an O3 and hydrogen alpha filter for nebulae. And then we'll get into that a little bit more. And then it also has a solar filter, which I put in my pocket, whatever, so you can take images, nothing like we just saw, but still pretty kind of cool. So, and the whole thing is extremely lightweight. Even with the case, it weighs 8 pounds. That's it. So, all right. So it's for deep sky imaging, not for high resolution images of planets or anything like that. But anyway, and let's see. So the way it works is it is an alt-az mount, as you can see, and it takes a series of 10-second exposures and stacks them together. So that's it. And it does have an anti-dew feature, which I didn't use initially, but it's been kind of handy lately. And anyway, turns on a little heater. The battery lasts for about 6 hours unless you're using the dew heater. So, and you can charge it, of course, if it's running. So no big deal. You can also capture videos, which is kind of a nice feature. You can do this during the day for terrestrial images, but also for solar and lunar images. And we'll talk a little bit about that later. And it does capture raw frames, so you can do your own processing, or even could, I presume, do some photometry, although I haven't tried that. So, all right.
Okay, I got a question for you.
Yeah.
I see you got dew heater included. Have you used the dew heater?
Yes.
Does it work okay?
Yes.
Okay.
Yeah. I didn't use it initially, but because I didn't really need it. But yeah, when I went down, yeah, there was a bunch of dew on it. You just turn it on. It's here, so works great. So it kind of has everything you need for basic operation. But if you do want to buy them, I did put this one on here. Most people buy this because you do need to make it level before you start looking for the sun or the moon. Otherwise, it doesn't really matter that much. But and I already mentioned about the that's recommended a tablet. And then there are some other tools that other people use to help with focusing or other things. I don't use them. I haven't found them to be necessary, but those are options if you want. There is the app itself connects to its own global community, and there are lots of Facebook groups where people post many, many images of these things. A lot of the users on Facebook post-process the images with tools, but the ones I'm showing you here are using they're straight out of the C-Star, partly because I'm too lazy to actually do anymore anyway, and I don't really have time for that. So anyway, so I got this thing back in February, and it was the full moon, so but it could still get some pretty interesting images, but of course I was eager to take it out somewhere else. So here we were at Big Bend in spring break, and here's an image. It looked definitely a little bit better from Big Bend than our backyard, although it's pretty credible in the backyard. But Horsehead Nebula here, and then also there the comet Pons Brooks was going by, so we were able to take a picture of that. Now you'll notice if you look closely that the C-Star still is tracking at sidereal rate, so you'll see that the coma of the comet is somewhat it's blurred after a while, but it's still pretty cool image. So
Hold on.
Yeah.
So wait a minute. So this comet image, is it like a comet setting on this thing?
no, you just there's a catalog, and you say what's up tonight, and you can also search for it by name. But anyway, in this case, this comet's there, as it'll tell you, 12P Pons Brooks, and you just select it, and it'll go to it. So.
Yeah, because the reason I asked is because usually either your stars are smeared or the comet's smeared.
Correct.
But in this one, your stars and your comet look good. How long did this go for?
So this one's only 8 minutes. That's why. So if you look closely, it's smeared a little bit. The comet.
Well, still, even for 8 minutes, that's pretty good.
Yeah.
I wonder if it does something funny because
Well, it's stacking, but it still might do something a little funny in terms of it. Yeah, it might try and overlay, but certainly overlaying the stars. Yeah. Well, I don't know. I don't think it really does much different.
you don't think it did anything?
I don't think so.
Really?
I mean, if you look at it, you can see this movement.
8 minutes.
Yeah.
So you're saying the stars are smeared or the comet's smeared?
The comet is smeared.
The comet's smeared. Okay. Hold on.
That would make sense.
Does anybody believe this? Chris, do you believe that?
It's pretty amazing.
Are you paying attention?
Oh, yeah.
Okay, look, that's 8 minutes on a comet, right?
It's probably 8 minutes of 10 second subs, right?
Yeah, 10 seconds. Yeah.
Hold on, what?
I think the optics on it are like 50 millimeters.
Well, that's the diameter.
Yeah,
but it's still
wide
wide.
field.
What's the focal length?
F5.
Yeah, it's F5.
So that makes it 250.
Yeah. So it's like a finder scope, right? It's a finder scope with a camera.
Okay.
And that's how you did 8 minutes.
Okay,
Yeah, but I agree, the comet and the stars both look very sharp.
I'm having trouble with that because I've done this. Either one or the other is smeared. 250 millimeter focal length. I don't know, 8 minutes.
What was the sub exposure?
It's 10 seconds.
Oh, 10, they're only 10-second subs.
Oh, 10 seconds. Yeah, but still, either the comet or the stars would be smeared, right?
Yeah.
Comet looks a little
smeared.
It may be stacking it both ways.
It looks wide. Nice picture, Paul.
What I'm trying to figure out is doing something because it's a comet. Because when you process a comet, you process it differently than a deep sky object.
But you said he was tracking the stars, I thought.
Well, you tell it you're doing a comet, but I don't think that it's really doing anything different processing, but I'm not sure.
Okay, I'm gonna cogitate on that for a little bit.
All right.
Okay, thanks.
And, of course, I would love them to update the firmware so it tracks, starts tracking the comets and stuff, but I doubt that's going to happen. But they do, anyway, you do get firmware updates and about once a month or so. All right, then from Goliad State Park, I got there late at night and I took this, really just one image before turning in, but M51 was pretty cool. So still one of my favorite images from the Sea Star. So, and then in Cedar Hill State Park, we were there. This is right before the total solar eclipse. And so just one of the better images I took of the Orion Nebula. Again, when you select a target from the catalog, then it has a little icon telling you, a green icon telling you should use the nebula filter, and it actually applies it automatically. If you just go to, then you have to hit the button to go there, to apply the filter. But anyway, for the most part, it at least suggests to you. If not, then you can do it. It'll even do it just automatically. And then I put together a series of exposure times. So everything in this 1 to 15 minutes, so you can kind of get a feel for how it goes. And the second one, it's the 5 to 25 minutes. So some of the pictures, some of them are repeated. So once it gets beyond 15 minutes, I don't know, any changes are pretty subtle to me, but that gives you an idea of how it works. And then this was the total solar eclipse, Waxahachie in Dallas. Yeah, go ahead.
What's the limit on the exposures that you can take with it? I know they're 10-second images, but can you take
Indefinitely, really,
6
but
hours of?
you can, and there are people who they'll do the raw images and post-process them, and they'll do days worth of images. I get.
Exposure time, 10 to 30 seconds. Just section of 10, 20, and 30 seconds.
Oh, is that?
And not to do the 20 or 30 seconds because it's odd azimuth. So it will kind of
Field rotation.
Yeah, you field rotation.
So the recommended is 10 seconds.
You got one of
But
these?
you-
too?
Yeah.
Oh, another one, okay.
But just with like other telescopes, you can take hours of individual.
Is it 999 photos you can ask it to take on target?
No, you just do time. So you just go until you hit the button to stop. So, and it just adds them. So.
Yeah, but he's right, you're gonna field rotation. Real quick.
It's stacking and rotating images.
I'm actually waiting to do not do any wedge. It can actually mount to it, so you can software updates for that. But
Okay, so that's stacking and rotating both?
yeah.
Okay, all right.
Well, yeah, I mean, it's obviously electronically rotating it. So yeah, you can see some field rotation eventually if you at the edges of the field. It's not evenly exposed, but it still stacks the stars. So it's all software. Yeah. So I just put together some images here just to show, you can get some decent images of the eclipse, and then it has a feature here. Let's see if it plays here. So there's a time lapse, which is I thought kind of fun, but I should have done the much shorter time between the different steps, but it was still kind of cool. And you can see in the center frame, if you look closely, they had done an update that lets you change the gain, and so this is still with the solar filter, but you add the gain, and you can see the prominences there a little bit. So, and then this is what it looks like just with the solar filter. No, not without the moon in front, whatever. But anyway, this is whenever we had that massive solar region, active region 3664 produced all the solar flares, et cetera. And here's an image of the moon. So it's not obviously high resolution, although you can certainly show some of the different colors on the moon, the high areas and different colors of the Maria, different Maria, et cetera. So we just tell it to go look for the moon, and it goes and it does a little search algorithm to find it. It knows about where it is because, again, you tell it from your phone or your device anyway. It knows what time it is and where you are. But and then it has to be level, and then it searches for it. And sometimes it doesn't find it, and it does help a little bit if you look somewhere else first, so it knows it doesn't horizontal. It does the calibration first, and then it kind of knows where it is. So that's another option.
So is the app in this particular instance one from your phone, or is this on a tablet? I'm just asking for the width.
So it's always portrait. Let's put it that way. And so it's the same either way. But this particular one, I don't know. April is probably a tablet. I don't remember. But it's always this. It ends up being the same. All right. And then it does have an option to do raw video stacking, and we're in those solar and lunar modes. I've tried that. I didn't really think it made the image all that much better. So maybe I'm doing it wrong, or maybe it doesn't reject any images or something like that. But it does looks different, but it doesn't really. I didn't find it had a whole lot of resolution. But there are those features, and then yeah, so. And then, so yeah, you can do the video, which the video looks cool, but then you can also do the stacking. And then back in League City here, tried some things. So here's a relatively bright supernova. It's 12th magnitude, 32 million light years away, but anyway, easily picked up with the sea star. So from the backyard, barely over the fence and barely over the house, the house next door. So that was kind of cool. And then there's a feature that it has that you take your image, but then you can also mark the objects as long as it knows what they are. It doesn't mark comets or anything that moves pretty much, but it does things that are regularly in its catalog. It will mark where they are. And it has an interesting feature that you can, when you stop an exposure, so you might do this for a couple of reasons. One is, just in case, you've spent 20 minutes on it, you don't want a satellite to go through and ruin the image or something like that, so you might stop it. Or you might say, well, let's see what we can do with this. Or in this case, I take an image, stop it, and then I click to mark, and then I say start again. Well, you say start again, and then it says, do you want to continue or restart? So in this case, I said continue. So it just adds to the image that's already being processed. And in this case, you can mark it, and then now you have two images very quickly. So, another image very quickly that says what it is. So it's kind of handy little feature. And then here's an image a couple images where and showed where the comet moved in 3 hours. So the comet does move, but different. These are obviously different images. So that's. Oh yeah. Thank you. So it moved a little bit, and a feature I would like them to add would be, here you just take an image and go back a few hours later, take another image. It'd be kind of cool if you did kind of some long-term time lapse. That would be kind of a neat feature. So this comet, I guess, is going to be really cool in October, I think it is. We'll see it more. But anyway, and then so TCRB, and the recurrent nova everybody's looking for. This is it doesn't have TCRB in the list. It does have certain stars, but it's really just named stars that are that's bright stars that it's using for alignment or something. Double stars if they happen to be in that same list. TCRB is not in that list. So, obviously just go to something that's nearby. I can't actually see. I see 4587, but but it's a convenient way to find TCRV. That's really it.
So when do you think CRP is going to?
I don't know, very soon, I guess. We'll find out. So, yeah, I have a series of images where I keep going to look for it, as I'm sure most people do. So, anyways, this is just the Lagoon Nebula again from our backyard. So, pretty fun to be able to do that. And the Eagle Nebula. So, yeah, just kind of neat. So I just had my own perspective. I brought my book here this was really kind of one of the first things that I started on. And so this was, I picked this up at a Walden Books, which is extinct. And for my Wildman back there, this might as well be the late Cretaceous period. But anyway, anyway, bottom line is this book has a set of color plates, with the different things. And of course, this is all emulsion photography, which, all guided and everything like that. Super cool, a lot of work. And at that time I had a 60 millimeter refractor, and liked looking at things, but they of course didn't look like that in the pictures in the book. So I always wanted to be able to take some images, and I still have a planetary camera that we've taken some pictures of the moon with and all that. But this was the first real forced foray into more serious, I guess it's still maybe not very serious, but anyway, astrophotography, and it's pretty fun to go and see these things. I have worked on ground-based telescopes, but I'm not trying to compete with, if you go to look at the Large Monolithic Imager on the Lowell Discovery Telescope, they look an awful lot better for obvious reasons, but that's a 4.3 meter telescope, but this one I can pick up and carry around. It's pretty fun. So, and some of the pictures that we get are, at least comparable to, in some ways, a little better than the emulsion photography. Most of it's with an 8-inch SCT from, the 1980s. This is pretty decent, actually. And yeah, so that's kind of where we are. I think it could be kind of cool to take it to. I know some people have done this to star parties and things, but we'll see. When we were at the national park, we showed just the people who were randomly there. Here, would you like to see a comet and whatever? And I think they were puzzled by the telescope. Is it really a real telescope or not? But anyway, it was cool. So, I put down, my thoughts. The Sea Star is, to me, what's not to like about it. It's super portable. Even if the sun is going in and out of clouds, and I would not take a heavier telescope out, because it's like, I don't know, well, I just pick this up. I have it upstairs, and I just walk downstairs and set it up, and I can take can be imaging the sun in really a couple minutes. So it's, kind of low effort in there. And I just, to me, it's pretty amazing what can be done with a 50 millimeter optical system, which is, even smaller than my 60 millimeter refractor that I had when I was a teen, and still have it. Okay. And but with some good software, et cetera, you can do a lot. Now there are some things, the elapsed time is not the same as the integrated time, right? It takes a little, it does reject some images, so it takes a little while to get some of those. The time you see there is the integrated time, not elapsed time. So it's not perfect, but by any means, but it does pretty well. And I had my experience. Everything I've done, somebody else has done with the Sea Star already, and published it. They put it on Facebook or whatever. But anyway, that's that. So I mentioned proper comet tracking. That would be something I'd like them to do. The time lapse, maybe improve the stacking of the raw video. I'm not sure actually if that's possible or not. And one thing that I would like is I would kind of like them to mark north on an image. It's actually mostly with the solar images. There's nothing, if you just take an image, and I'm usually taking it after work at night, there's nothing that shows which way the pole is. I take pictures over a few days, and you can see how it's rotating. But if you're just looking at an image, you wouldn't know. There's nothing to orient you on the sun. So in general, that'd be nice to have. So wish list for the next product, obviously a larger aperture, which would mean really going away from the refractor design. And then obviously a higher resolution sensor. It's a 2 megapixel sensor. So, but still, for what it is, I think it's pretty exciting. That's been my experience. And so I did kind of as a result of all this, I started putting images on a website. So this is what it looked like when I did this presentation a few months ago, but this is my first foray into making a website and whatever. So we'll see how it goes. But right now I've imaged 87. I have images of about 87 of the Messier objects, and of course many other things. But there are people who months ago have done them all. So whatever. But anyway, it's kind of fun for me to put things up there. And so I can go back and see what they look like. And hopefully other people will eventually too. So that's it. That's all. Any other questions?
Yeah, I have a question. So a couple of slides ago,
Yeah.
you said you worked, you don't have to back up, it's okay. You
Okay.
said you worked, no, it's okay. You worked on some ground-based telescope projects.
Yes.
Which ones were those?
So I was software engineering manager for the Discovery Channel Telescope project at Lowell Observatory, which is now Lowell Discovery Telescope. They just renamed it. So, so that's a 4.3 meter telescope in Happy Jack, Arizona. And the other one is still being worked on. So I did some software for that, but that is at that time it was the LSST telescope project, but now it's actually the, let me remember what the actual name of it is now.
But you're not working on that now?
No, I don't work on that now. But anyway, that's being built in Chile, and it'll scan the sky.
Right, but you did the Discovery telescope in Arizona.
Yes, correct.
Vera
Rubin Observatory. Thank you. Sorry, that's terrible. But yes, yes, Vera Rubin Observatory. Yeah, that's what it is. So
So
anyway,
you've gone from that to a C-star.
yes, right. I can't take the other ones home. So anyway, yeah, exactly. So yeah, I mean, when I worked at Lowell, one of the astronomers, I really want to get a telescope and look at things. One of the other ones said, well, you can go out at that time. Anderson Mesa was where the other telescopes were. So you can go out there anytime. Well, I did go out there occasionally, but yeah, there's something about being able to do your own imaging. That's kind of fun. So, yeah. Any other questions, comments, suggestions?
Comment.
How much does that thing run these days?
It's this price is $499, a little less maybe on sale. But it's most of it's $499.
With the tripod?
Yes,
Really?
carbon fiber tripod. I mean, this doesn't come with it. But everything else does. All the filters and everything.
Any others? No? Okay.
All right, thank you.
Thank you. That's great.
Okay, I think we need to start a C-Star users group. What do they call that? Special SIG, special interest group, right? We've got so many people buying these things. Alrighty. Okay, David couldn't be here tonight, but this is David's Star Party news, which I will try to give. One star party in the past, July 13th, the Hack Winery. I got some pictures of that coming up here. Coming up, August 16th, another Hack Winery event, also September 14th. And then September 27th to October 5th is Okie-Tex Star Party. So there's about 5 of us that are talking about going to Okie-Tex this year. And if anyone else is interested in going, let us know so we can kind of all communicate with each other and know who all is going to be there so we can look for you. But Okie-Tex is arguably probably the best star party in the United States. When I've gone around and asked people, what is your favorite star party? Majority of people say Okie-Tex. So I've been there a couple times myself. It's pretty good. If you go, prepare yourself for weather. You know, Oklahoma, they just love weather, but it can be it can be pretty exciting out there living in a tent at this place. So, but if anyone else wants to go with us, let us know, and we're gonna have a blast, I hope. Okay, then October 4th is Hack Winery again. Then October 12th is going to be the Observe the Moon night out at the Georgia Observatory, which used to be the Astronomy Day, but now they call it the Observe the Moon night. Then
Where actually is that for the newbies here?
the Georgia Observatory is at the Brazos Bend State
yeah.
Park.
Okay.
There's an observatory out there.
I run the big dome out there, so.
He's the guy. He runs the big dome, not the little dome, the big dome.
Research, I'm authorized on the West Dome.
Is that the big dome?
No, that's.
No.
That's the little dome. Little dome, big dome.
No, I run the 36 and the 11-inch refraction.
So if you go out there, you're going to see these two guys. There they are. You guys going to be there on that night?
I don't know.
They don't know.
I'll be there.
You'll be there. Justin will be there.
I might even bring my laptop with the virtual moon atlas. If anybody's ever heard of the VMA, maybe we can see some good details on the moon.
Oh my goodness.
I've even viewed a few of those volcano archipelagos, the archipelago domes, like the Vesuvius domes, the Sea of Tranquility, because there's a lot of those volcanic dome archipelagos, thousands of them.
You did that.
Brandon?
Can you do it correct?
You check the date on your calendar.
Can you do?
2022,
October 12th?
Very top line.
very top.
Oh, you know what? I didn't make these slides. My name's not David.
Oh, here we go.
I know.
It took 2 years to come to you.
You know what? I didn't even catch that. I actually do correct the errors in this, but I didn't catch that one. Thank you very much. The Masood family got us there on that one. All right. That's what you get when you're a college professor. You see those things. And Chris, or sorry, Brandon, you were going to say something?
I was just reiterating what they said.
You guys. Okay. You're going to find other errors in these things if you look for them. Okay. Anyway, next one. Okay. Fort McCavett, October 24th to the 28th. Okay. So Fort McCavett's free. And if you guys don't know where Fort McCavett is, you go out past San Antonio, go past Junction on I-10, way out there. It's 365 miles from here. And it's all free. Dark skies. It's actually the darkest of the skies. Well, actually, I think Okotoks is the same darkness as is Fort McCavett. But it's a if you know the Bortle scale, it's a low Bortle too. So it's very dark there. And nice thing about Fort McCavett, it's absolutely free. You can go out there and have a great time. And this time it's going to be Thursday, Friday, Saturday, and Sunday. So you can actually stay out there 4 nights rather than 3. And then the El Dorado Star Party, which is just a few miles down the road, then you can get in your car and then drive down on the 28th and go to the El Dorado Star Party and stay there from the 28th to the November 2nd, which is what we've been trying to do for a long time. We've been trying to get these 2 star parties right next to each other because they're geographically in the same area. And a lot of people say, hey, if I'm going to load up my car and go out there, I'd rather stay out there for a while. So now we got it set up so you can go to Fort McCavett. You can get in your car and go to the El Dorado Star Party and have a week and a half or so of astronomy. And I know several of us are going to Fort McCavett, so we will be there. Then November 1st is another Hack Winery event. And then, okay, November 9th, you guys in last row. Okay, so a lot of people, I'm talking to you, Audrey, pay attention. Okay, yeah. Anyway, a lot of you guys keep saying, oh, I want to go out somewhere and look through a telescope, right? Look through a telescope. Okay, this last one, this is at the Evelyn Meadow. You guys didn't go last time. You need to go to this. Okay, so on November 9th at the Evelyn Meadow Library, it's open to the public, and anybody wants to go out there and look through a telescope, you can come out there and you can look through one, okay? And I get a lot of people saying, when are you guys going to have an event where it's just open to the public and everybody can go to it? And I don't have to drive 300 and 400 miles to go. This is it, Evelyn Meadow on November 9th. So please come to that if you want to look through a telescope.
No,
Seabrook.
it's in Seabrook.
I'll be there.
I bet. I don't believe it. I'll believe it when I see it.
It's about 6 miles from here.
Hey, bring your telescope too.
Okay.
Yeah, bring your telescope. There's a bunch of people who would love to, not me, but other people would love to show you how to use it. I just want you to leave me alone when I'm there. But there'll be other guys like Stan. He's pretty nice. He'll probably show you how to use your telescope. And B and Jerry, they'd probably show you. So, but it'll be fun. And we have like a great time out there, but you guys should come to it. All right. Any questions about those events? I hope not. All right, here's some pictures that David took at the Hack Winery event on the 13th. He said it started out cloudy, but then it opened up around 8:30. Got to see the moon. Thanks to Connie and David and Chris Randall and Bob and Leslie Eaton were there. Had 3 telescopes and 1 set of binoculars and some chickens.
They start having food there yet, or they're still like snow food?
I have no idea. Do you know?
Chicken dinners.
Are you saying no? Oh, you don't know? Yeah, that's the dinner right there. Chicken dinner.
Yeah, in my cooler.
Yeah. I don't know. I mean, sometimes they have food, sometimes they don't.
I know, they're like, they're going through a bunch of stuff. There is wine though.
Yes, there is. All righty, some more pictures showing the sky wasn't so great. And then they got some clear skies, got kind of a borderline picture of the moon. And meteorologists have, okay, you guys can read David's joke there. You know, David always puts a joke at the end of his Star Party newses, so that's a good one. All righty. Okay, so that's about it except for door prizes, which we're going to do. Everybody get a door prize ticket? Anybody not get a door prize ticket? Did you two get a door prize ticket? All right, okay. Okay, so next month, September 13th, Leonard Ferguson is going to tell us about the Europa Clipper mission, and that's going to be great. And when we get after door prizes, we're all going to tear up to Mod Pizza and have a nice time there. So next up, who's got the door prize bucket? We are going to do door prizes. Thank you. Thank you, Grant, for being our doorman today. Part-time doorman. And ticket giver. I got so distracted by Rosanna Howard. I don't know if you guys saw that, but that lady that came up there was the young lady who gave a presentation from the United Kingdom a couple months ago, and she's actually here in person. So I got kind of distracted by that. Didn't get the door prize out. But I don't know. Okay. All right. So look at your ticket, see what your number is. And first one ends in 764. 764. Is it you? Come on down here. Woo-hoo. Oh, wait a minute. I gotta find something good for you. All right, hold on. Okay, let me find something good for you. Let's see. Okay. Here's what I got. I've got these patches here that's, Axiom Space patch. That's kind of cool, and a pin. Or we got this Apollo 11 notebook where you can write stuff in there. That do anything for you? Not yet, huh? Or I got a map of Saturn. I got a map of Jupiter. You don't want these. Or I got a map of the moon. What do you think? It's difficult to decide. You got to pick one of them. You want this thing? You can write stuff in it. You want that? Okay, you take that. All right, very good. All right. Next number, 774. Reed, come on down here. Oh, I got the perfect thing for Reed. Where is it? I probably won't be able to find it fast enough.
ZWO keychain.
Oh, shoot. You knew what I was going to find. I can't find it. Oh, there it is. No, that's not it.
Uh-oh.
Okay, forget it. Hey, look at this. I got this is a capsule squeeze toy. You know, you're stressed out at work. Yeah, squeeze toy. Or you got a moon map, Jupiter map, Saturn map, or I love radio astronomy socks.
I like the moon map, I think.
Okay, then. You got it.
774. There you go.
All right.
Thank you much,
I
sir.
believe you. Next one, 763. All right, Linda Bridge, come on down here. Linda, are you stressed out at work? Do you need a capsule squeeze toy? Lockheed Martin, see?
Oh,
Saturn
I
map.
would squeeze that a lot.
See, there you go. Or a moon map, or I love radio astronomy socks. Will ya? You know how long I've been trying to get rid of these?
Really?
Yeah. Okay. All right, radio astronomy. I love radio astronomy. You need to see what's in our backyard sometime.
Okay.
Yeah, okay. I'll send you a picture. Okay, 765. That's pretty close to her number. 765. That you, Chris?
Wrong way, Doug.
Any 765s? Is it him? Come on down here. Oh my goodness. I got just the perfect thing for you. Come on down here. Come on. Yeah, bring that with you. That's pretty cool. There it is. Okay, we're gonna do one more door prize after this, and then we'll skedaddle. Do you want to have one that's kind of like your brother's, but it's got a NASA and Artemis and all this on it? You can draw it? You love drawing? Why don't you take that then? Okay. All right. Okay, I'm gonna shake these up real good. I see some really disappointed looks on you guys' faces up there, like you wish you could win one of these door prizes. She got the socks though, so you know that's it on that one. You know, we've had actually the other socks are actually very popular, but not that. Knock your socks off. Okay, 773. Audrey, I'm trying for you. Is this yours? No. Oh my gosh, come on. 773. Okay, you guys get another chance. Let's see if I can pull Audrey's number. Okay, 770. Mark, come on. Mark, are you stressed out at work? Do you need a capsule squeeze toy? A Saturn map? A Jupiter map?
I'll do the squeeze.
Do you really?
Yeah.
You got it.
I'll take it to work.
You can't believe how long we've had that thing. Okay, very good. All right, that's it. See you guys at Mod Pizza in a few minutes. We're going to have a great time. Come back next month. Trevor go? There he is. Yeah.
So I had 2 hour-and-a-half things with my buddy Chris from Takahashi. Answered all your questions. Oh yeah, that's really effective.
Yeah, not you.
Yeah.
So what happened?
Answered all the questions. Here's the good part, okay, which is really kind of exciting. He actually likes the fact that I research stuff and go ask him a bunch of questions. His favorite, he's got 8 telescopes, right? His favorite telescope is exactly what I have. And everything he's telling me to buy, he goes, it's light. He goes,